1 atmosphere of pressure is 25 degrees Celsius, and all the concentrations are 1 mole. Okay? So in most of chemistry, standard conditions are at 25 degrees Celsius. But if you do gas laws, okay, gas laws, that standard temperature is 0 degrees Celsius, okay? Which obviously you can't do solutions under standard temperature of 0 degrees Celsius because the water would freeze. And why they picked 25, I don't know. They must have been in the Bahamas. Most labs are about 20 degrees Celsius, okay? I don't know, maybe they played rock, paper, scissors. I'm not sure, but they picked 25. So when you see this symbol of delta HF, okay, so it's enthalpy like we've been studying, but the F stands for formation, and when you see that little circle up at the top, that just means under standard conditions. So unless you're specifically told something differently, that's what you're going to use, okay? Standard conditions. So the data table at the back, that Appendix C that lists all of those thermodynamic values of enthalpy, entropy, and heat free energy, all of those are based upon standard conditions of 25 degrees Celsius, and that's what you just have to roll with. Okay, now here's the important part of this. This is associated with the formation of a compound from its elemental substances, okay? There's a whole bunch of different ways you can make different things, but if you're talking about what's associated in terms of standard enthalpy of formation, it's only based upon the production of that from its elemental form. So, simple example. You want to make aluminum chloride, okay? There's a whole bunch of different ways you can make aluminum chloride. But if you're talking about the standard enthalpy of formation, you would take solid aluminum and you would react that with chlorine gas, and you would make aluminum chloride. Okay? Now, there's different ways you can make aluminum chloride. You could do a double displacement reaction between aluminum nitrate and sodium chloride, and you could make aluminum chloride as a precipitate. You could make it that way. Okay? You could do maybe any number of different substitution reactions where you can make this. You could do a redox reaction to make aluminum chloride. But if you're talking about standard enthalpy of formation, it's always based upon the substances that you have in the elemental form to make it. Now, here's the other tricky part about this. We need to balance this equation. Okay? So when you balance this equation, what does that look like? 2, 3, 2. Right? There's the Chem 1 version of this, right? 2 aluminums, 2 aluminum, 6 chlorine, 6 chlorine. Boom, we're good. But when you write this in terms of standard enthalpy of formation, you divide it out so that whatever is in front of the product that you're making, in this case aluminum chloride, you need that coefficient to be a 1. So this is how you get the fractions out of this deal. So you're going to divide all of these by 2. So the standard enthalpy of formation reaction would be 3/2 Cl2 yielding AlCl3. So you balance it just like you normally would, and then you divide it so that that product has a coefficient of 1. Okay? So one of the things you're going to have on your assignment is the production of like sugar, C6H12 or C11H12, whatever that is. So you build it out of its compounds, you balance it, and then you divide it so whatever that coefficient is in front of the product has a value of 1. Cool. Now, what I'm going to do next is a very long, complex process. Don't flip out. I'm not going to expect you to do this in any way, shape, or form. But it gives you the background story on why the shortcut works. Okay? So I'm going to show you the long process. I'm not ever going to expect you to do the long process. But you need to understand the long process so that the shortcut makes sense. Okay, so don't flip out and go, oh, Mr. Burkett, we're going to have to do this on the quiz? No. Okay, I'm telling you straight up. But you need to understand the process and how it works. So, here's what we're going to do. We're going to do a reaction. We're going to take 4 NH3, which is a gas. We're going to react that with 7 oxygen molecules as a gas. And we're going to make 4 molecules of nitrogen dioxide and 6 molecules of water. Okay. So here's the reactants. You have ammonia, NH3. You've got 4 of these. You got your oxygen. Okay, so here's what's going to happen. You're going to break, this is going to be important. We've got to break bonds. We've got to break the bonds. You break the bonds, input of energy, outflow of energy. Input. Okay, so I'm going to break these bonds. So now we've separated these bonds. We put energy into it. So then we're going to make NO2, which is going to be a nitrogen and a couple oxygens. We've made this. And then we're also going to make water. All right? So we're going to break bonds, and then we're going to form bonds. Okay? And the difference between those energies is determined whether it's endothermic or exothermic. Okay. So what we're going to try and do out of this equation is that we're going to try and figure out how much energy is either released or put into this reaction. So we need to find delta H for the whole thing. So like I said, do not flip out and go, Mr. Burkett, we don't have to do this. No, but I need you to show you the process. So here's the process. So we're going to take the 4 NH3s, and we're going to do like the reverse of the synthesis reaction. We're going to take the 4 NH3s, and we're going to break that up into its constituent parts. So if you take those 4 NH3s, that's going to break up into 2 nitrogen molecules and 6 hydrogen molecules. Okay? That required an input of energy. So imagine this. You've got your NH3, right? You've got 4 of those. We're going to separate these out. And we're going to make a bunch of hydrogen, and we're going to make nitrogen. Okay? Break the bonds. Okay? And then we're going to reform them into its constituent parts. Now, the oxygen is simple. The oxygen is already in its elemental form. Okay? It's already as oxygen. We don't have to do anything with it. So this is going to be important. One of the key things to remember is that the standard enthalpy of formation of the elemental substances is 0. Okay? Mainly because they're already existing in their elemental form. We can't make them out of any more of an elemental form because in its elemental form. Okay, so those are just going to be 0. So the oxygen molecules, we got 7 of those. Those are just going to stay. Okay, we got these. So those are just going to stay as 7O2. Now we got to form the products. So we're going to take some of the nitrogen, and we're going to take some of the oxygen, and we're going to combine those into the 4 nitrogen dioxide molecules, okay? And then we're going to take some of the hydrogen, and we're going to take some more of the oxygen, and those are going to combine to produce my 6 waters, okay? So we got the idea. So they were together, we separated them, and then we're going to recombine them. Got this. Okay. Now, here's what I need to figure out. Here's the long process. Okay? Here's the long process that you're never going to have to do. But I need somebody to go to Appendix C in the back of the book because I need some thermodynamic data. So, here's what we're going to do. We're going to take the 4 NH3s. So find ammonia. Find the NH3 value. And that is going to get broken into 1/2 N2 plus 3/2 H2. So what I need from the back of the book, and understand why I did this, because of the fact that with this, in terms of your NH3 itself, the decomposition or the formation of the NH3 from the molecules is NH3, and this is why I have the 1/2 N2, because if I take 1/2 N2, that gives me 1 nitrogen. I take 3/2 as my hydrogen, that's how I get my 3 ammonia. But this is going to take place 4 times, okay? So what's the value for the enthalpy of formation of ammonia? What's that value in the book?
Negative 45.94.
Negative what?
45.94.
Negative 45.94?
Yeah.
Okay, now, that is for the formation of ammonia from its elemental compounds, okay? But that's not what we're doing. We're decomposing ammonia into its elemental compound. So we got to flip the sign, so we got to make this positive, and it's going to happen 4 times.
Yep.
So somebody take 4 times the 45.94. What do you get?
183.76.
183.76. Okay? And that's technically kilojoules per mole. So here's what this number means. If you take, and this is always per mole. So if you have the 4 moles of ammonia, you have 4 moles of this stuff. That's a lot of particles. And you're going to take this and you're going to break it apart, and you're going to make hydrogen and you're going to make nitrogen. This is how much energy you would have to put in that's associated with the decomposition of the ammonia into its elemental substances. Yes?
Does it not make energy, though, when it forms the bonds?
But it does, but that's all taken into account. Okay? And the same thing is going to happen. If you started with nitrogen and hydrogen, if you started with this side and you made that, this is how much, but that would be a negative value if it was released, because it would be negative because the formation of it releases energy. But the decomposition of it requires an input of energy. Okay? That's why that's a positive value. Okay, so we got that. Now, we're going to make NO2. Okay, so we're going to make NO2. So to write that reaction, that's going to be 1/2 N2 plus O2 yielding NO2. But again, that's going to happen 4 times. So somebody look up the thermodynamic data for the production of NO2. What does that delta H equal?
33.84.
Now, am I going to leave that as 33.84, or am I going to make it a negative value?
You leave it.
Why?
It's in the product.
Because this is for the formation of it. This is what's happening. I'm making this stuff. I'm not going to switch the sign because I'm making this stuff. So what was that value? Say that again.
33.84.
33.84. So somebody take 33.84 times 4, because that's got to happen 4 times.
135.36.
135.36 kilojoules per mole. Cool, we got that one done. Okay. Now, the last one we have is the water. Now, this is what we talked about yesterday. Water exists as 2 forms on that chart. It exists as gaseous water, and it exists as liquid water. Okay? They're different thermodynamic values. You have to pay attention to water, whether it's a liquid or if it's a solid. Okay? Vital, liquid or gas. Okay? So this is going to be liquid water. That's why I've got that L on the end of it. It's going to be liquid. Cool. So this is going to be H2 plus 1/2 O2 yielding H2O liquid. and that's going to happen 6 times. So and again, this is weird. It's not listed under hydrogen, it's listed under oxygen. So when you find this thermodynamic data, you have to go to the oxygen section and find the liquid water. So what's the value for water?
Negative 285.83.
5.83, and that's going to happen 6 times. So what do you get?
Wait, Berkey, if you can write in the margin now.
1.
Huh?
It's like you, spot that you usually can't write it.
I don't know. This is a true story. First block, this thing got possessed. No, it did. And I'll show you why. Hold on. Nope. That's it.
How often do you start doing it?
Okay, so this is where this got weird. When I drew this circle, that circle was in the middle, and then like 5 seconds later, it randomly like shifted down. Like I didn't see it. My kids were like, the circle moved. Okay, it did. And this, when I wrote this, it was up beside that. And then like 5 seconds later, it just randomly shifted down. So it's like this thing is possessed today. Maybe just because I'm wearing a t-shirt and the universe is out of, the feng shui of the universe is out. So
It's an imbalance.
it is. It's like, oh, look, it's wearing a t-shirt. Whoa, this is bad. Okay. Anyway, so somebody takes 6 times 2, negative 285.83. What do you get?
1,714.
1,000 what?
714.98.
1,714.8.
98.
98.
It is negative.
Negative value. Okay. Now we're done. Okay.
Add them all up, bro.
That's just it. You add them all up. So somebody take the 183.76 plus the 135.836 plus the negative 1714.98, and what do you get?
Negative 1,395.86.
95 point what?
86.
0.86. So, is the overall reaction,
Yep.
is the overall reaction,
Foreshadow.
yes, endothermic?
No.
Big Ike's got it.
No, let's go with your answer.
Whoa.
Is the overall reaction endothermic?
Whoa. Whoa. No.
You said,
You said
No,
yes.
I said yes after like the question. Like, yeah, it is.
I did, oh.
No, this is exothermic burn because it's negative. Without a doubt, take it to the bank. Yep. Done deal.
Deal. $1 million on that one. Okay. Now, but does that mean that no energy was put into the reaction?
No.
No, but it just means overall,
More was released.
more energy was released. Okay. Now, but here's why I showed you this long, arduous process. Okay? So the reason I showed you this is what had to happen. You had to take the ammonia and break it up into its constituent forms. You switched the sign, that became a positive value, and that happened 4 times. We formed NO2. That's why we wrote it in its elemental forms. Those reacted to make the NO2. That was a certain value, 33.84. So the production of NO2 is actually an endothermic reaction because that's a positive delta H. Now, to make water, that's a very negative value. What life experiences have you had that reinforces that? With a negative value for water.
Whenever you make water, it's hot.
Crying.
Like when I make ramen burns, the steam it's hot and it burns.
Yeah. A watch pot.
What makes you do that?
The hard watch pot.
Mac and cheese.
No, I'm kind of smart.
They don't just magically spawn in.
Or that's all-
What happens when you blow up a hydrogen balloon?
Okay, alright. I've never done that
You
before.
said what negative
shut it.
experience? That's
So, when you blow up a hydrogen balloon, what do you feel?
Warm.
Warm, because it's an exothermic reaction. The chihuahuas go up to the top of the roller coaster, and they go, wow, on the way down. So they've got that energy and they give that off as thermal energy. Okay. Now, I am in no way ever expecting you to do this, but here's the shortcut. Okay?
Yeah.
Natalie thought you said a negative experience. She got crying. She's crying is a negative experience.
Oh, Valentine. Yeah.
Go on. Great, I'm going to have to go see my therapist. Thanks, Natalie. Brought up those repressed memories. I was kidding. Okay. So here's the shortcut. And this is actually what is on your equation sheet on this thermodynamic stuff. Okay? So if you'll notice, this is what you have. You have delta H F naught of the reaction. So this is for the whole thing. So that equals the sum of all the delta H's of the products minus the sum of all the delta H's of the reactants. Okay? Now, notice that you can do that with your delta H's. You can do it with delta S's, which are entropies. You can do it with delta G's, which are your Gibbs free energy. Notice that they all have the exact same form. It's always products minus reactants. Okay? Now, let me show you. We're going to do the same equation, but we're going to use this. It is always products minus reactants. Now, what some people like to do, because this data can get a little bit like blurry-eyed when you stare at it too much, some people will like take a piece of paper and they'll like line up whatever element that you're using so that way you don't cross over numbers, because this process in and of itself isn't horribly difficult. Usually you make a mistake because you write down the wrong number or you transpose some numbers or something like that. So in this terms of this reaction, so what I'm going to do, it's products minus reactants. So what I need, if you go to that whole reaction, okay, so my products are my nitrogen dioxide and the water. So I need the sum of the 4 NO2s plus my 6 waters minus the sum of my reactants. And my reactants are actually oxygen and my NO3. And your NH3, and there are, where's that? 7 waters and 4 NH3s. But which one of those do you not have to worry about?
Oxygen.
Big difference.
I was looking at the oxygen.
Yeah. So you don't have to worry about the oxygen because the enthalpy of formation of oxygen is 0. Okay? So you don't have to worry about that. Now, here's the beauty of this process. You don't have to worry about switching signs or anything weird like this. You just do this straight up. So you're going to come in here and go, okay, I need this sum. So I got my 4 NO2s, and what was the value of that NO2?
Checking.
33.84. 33.84.
Good boy.
So 4 times 33.84 plus my 6 waters, and the waters, where's that big negative value? Negative 285.83. 0.83. Minus, now this is minus, okay?
Minus.
I got my oxygens, but what's my oxygen value?
0.
You say. Don't have to worry about that. And then I've got my 4 ammonias, and my ammonias were, what was the ammonia?
Negative 45.94.
Negative 45.94.
And this is the gas form of ammonia, right?
Yeah.
Hey,
So, Now, this is why the beauty of this process is that you don't have to worry about like, oh, I'm going to reverse it and make it negative or whatever, okay? This is just straight up. It's just a pure mathematical thing. But don't switch the signs. Yes, Opie?
What's that in the parentheses, like the second parentheses?
Okay, this one?
On the second line.
Oxygen. 7 oxygen.
7 oxygen.
Yeah, but I don't have to worry about the oxygen because it's in this elemental form.
Okay.
So that's why I marked it out. Okay? So if you do this math, oddly enough, you're going to get the exact same answer. Okay? But the reason that I went through this long, arduous process of showing you that is because of the fact that technically that is what's happening. Okay? Technically, you're taking these compounds and breaking them into its elemental forms, and then you take those elemental forms and recombine them into something new. But here's the shortcut process. Now, here's the other thing, how this can play out. So let's say that you have, I'm just going to make up a number, A plus B yielding AB. Okay, 2, and maybe that's a 3. I don't know. I'm just making up numbers. Okay?
It's not balanced.
I know it's not balanced. But just take it. So what you might do is that you might determine the delta H for the entire reaction. In other words, you run this reaction and you do just like you did in the lab with copper sulfate, and you calculate the value of delta H. You see the impact that it has on the water. And you know for the entire reaction, maybe that's negative 185 kilojoules per mole. So overall, this reaction is exothermic. And let's say that you can look up in the table, and you can find out the table, you can find out what A is. And you can find out what AB is.
Oh, you can't be.
But if you don't know what B is, you can solve for it. It's an algebra problem. So if you know what the entire reaction is, you don't have to go through and find B separately. So if you know the entire reaction and you know parts of it, you can find the one that's missing. Okay? Makes sense. All right. So, Mark, can you stop that camera?